Now we are back again. So taking the Laplace transform of equation 10, right? If you take the Laplace transform and simplify, then you will get delta Fs is equal to delta Pgs minus delta PLs divided by d plus 2h upon F0 into s, right? Later what we will do, these are all per unit, so again and again here, so no, here we will not mention the per unit again and again, right? So but it is understandable, I mean from this point onwards everything is in per unit. If anything is real unit, it will be discussed. So this is your delta F. Now this one, if you simplify, basically delta Fs will be delta Pgs minus delta PLs into Kp upon 1 plus STP. That means actually Tp is this equation, right, whatever it is, this equation, a numerator and denominator you divide by d. So this can be written as delta Pg, s is understandable, okay, put it, minus delta PLs, right, divided by d, then divided it is also numerator, denominator also divided by d. So it will be 1 plus 2h upon F0 d into s, right. So we assume Kp, if you assume Kp is equal to 1 upon d, say let Kp is equal to 1 upon d and Tp is equal to 2h upon your F0 into d, right. This is your F0 d, this is your Tp. That means this equation can be written as delta Pgs minus delta PLs into Kp upon 1 plus STP, right. So Tp actually we call is a power system time constant. This is your, this one is your power system time constant, and Kp is equal to 1 by d is equal to gain of power system. This way we define this one, right. So transfer function for that, I mean generator and load, this relationship in between your generating power, load and that frequency deviation now has been completed, right. Now that means for this portion, I mean this equation, that equation 11, this equation you can make it like this kind of block diagram, delta Pg minus delta PL into Kp upon 1 plus STP is equal to delta F. So this way we can go for block diagram representation, right. So now, so block diagram representation of an isolated power system. Now what we have done, that figure 11 shows the block diagram of a generating unit with a reheat turbine. The block diagram includes speed governor, turbine, rotating your what you call rotating mass, right, rotating mass and your hold on, is rotating mass and load, right, appropriate for load frequency analysis. So we have seen that how to link that modeling, it is basically modeling how to link. So this is my governor, this is load reference set point, and we have seen also that your delta, your what you call that 1 plus STT, and it is your what you call this intermediate point, we are making your delta PV, because we have seen when we try to develop that your what you call reheat turbine modeling. So we have seen that delta Pg is equal to 1 upon 1 plus STT into your 1 plus SKR TR divided by 1 plus STR, right, into your delta E. So we have to make it in state variable form. So these two blocks split it, right, and in between this one state variable is taken, that is delta PV, and this is delta Pg is already output is here, and minus PL into Kp upon 1 plus STP, right, and that is your delta F, but this delta F feedback has come here 1 upon R, this minus, this is plus, right. So this part actually is a governor part, right, and this part is actually turbine part, and this is actually power system part we call, right. So this is rotor inertia and load together we call, this is actually power system part, power system, right. So, this is, if you look into that, there are 4 state variables. This is 1, this is 1, 2, this is 3 and this is 4. There are 4 state variable, right. So, we have to write down those equation in the state space form. So, that means x 1 dot, x 2 dot, like this. So, if you just 1 minute, if we want, I am just overwriting on it. If you want that your only non-reheat turbine, then this block should not be there. For this will directly be delta PG. In that case, you will have 3 state variable, this one and this one. If you do not consider reheat, if you consider only non-reheat turbine, then only 3 your what you call that your 3 blocks should be there, this one and this one, and this is actually delta PG output. This should not be there, right. This block should not be there. So, now state variable analysis, we have to go further, right. So, delta F we have taken x 1, delta PG x 2, delta PV3 x 3 and delta E is equal to x 4. Now, we have taken just one I am showing, other I think you can do it. One, assuming all initial conditions are 0, this is x 1, this delta F x 1, this is my x 2, this is my x 3 and this is my x 4, right. This is given in the next page. So, when you write this equation, state variable equation, right. So, you can write, and this is your load delta PL, right. So, you can write, I am writing here only on overwriting on it, I think it is, you can see it, x 1 is equal to, this is x 2 and this is plus x 2 minus delta PL into K P upon 1 plus STP, right. So, now if you cross multiply, so it will be x 1, plus, it is S x 1, here I am writing separately S x 1 into T p, but S x 1 is nothing but x 1 dot, right. So, it is nothing but x 1 dot into T p, right. So, S x 1 it is nothing but x 1 dot into T p, right, is equal to, this is your what you call, this is your K p x 2 minus K p into delta P L, right. Therefore, from here you can write your x 1 dot. If you write here from x 1 dot is equal to, this x 1 will go to the right hand side and divide by T p, it will be minus 1 upon T p x 1, right, plus K p upon T p x 2, right, minus K p upon T p your delta P L. So, this way you can write. So, that is why we have written x 1 dot is equal to your minus 1 upon T p x 1 plus K p upon T p x 2 minus K p upon T p delta P L equation, this is 12, right. So, one more I have to show you, because one derivative term is there in the numerator in this block. So, if it is x 2, right, first thing is that if it is x 2 and this is x 3. So, what you have to do is first, this is x 1, this is my x 2, this is x 3 and this is x 4, right. So, in this case what you will do, that x 2 is equal to your x 3 into this term, but there you need x 3 dot will come. So, first what you do, first find out x 3 dot. So, when you write x 3 dot, so x 3 is equal to x 4 upon 1 plus S T t, I mean this one, this block only. If you cross multiply, then it will be x 3 dot is equal to, because S into x 3 is x 3 dot. So, x 3 dot will be basically minus 1 upon T t x 3 plus 1 upon T t x 4, right. So, x 3 dot can be obtained from here, right. Next, next what we will do, take this equation, this is my x 1, this is x 2, this is x 3 and this is x 4. So, x 3 dot we have seen. Now, x 2 is equal to then this x 3 into 1 plus S K R T R upon 1 plus S T R, right. Now, if you cross multiply, it will be x 2 plus x 2 dot T R is equal to multiply this one x3 plus s into x3, that is x3 dot, that means kr tr into x3 dot, right. So, to eliminate this x3 dot, you have already got the equation of x3 dot is equal to minus 1 upon T T x3 plus 1 upon T T x4, that you will substitute here, that such the right hand side will be free of any derivative term, right. Then all x1, x2, x3 you will get, then x4 is equal to, automatically you will get it, right. So, this is for your x1, x2, x3, right, dot. Now, x4 is, this one is your x4, this one is your x4, this is x1, again I am writing x1, then we will go to that final thing, this is x3 and this is x4, right. So, here also x4 is equal to, you can write, this is my u and this x1 is coming here. So, here it is minus x1 upon r, right. So, it is basically x4 your what you call x4 is equal to 1 upon 1 plus stg, right, into minus x1 upon r plus u, right. So, just you have to simplify and you will get a cross multiplication and you will get the x4 dot, right. So, that is why we have written that x1 dot, x2 dot, your x3 dot and x4 dot. So, this all these equations 12, 13, 14 and 15, right. So, all these equations are written, but you derive of your own, right. Once you get all these equations, right, it can be written in the matrix form, that is your x1 dot is equal to x2 dot, x3 dot, all put in this matrix form. So, this is actually 4 into 4 matrix into x1, x2, x3, x4 plus your all will be all the first three equation no u is present. So, only last one is there, that is 1 upon T G U, and all the first equation that delta P L is present, all other equations delta P L is not there. So, all 0 0 0, this is also 0 0 0, this is 1 upon T G. So, this matrix we call, this matrix is A1, right, and this is B, right, and this is we call gamma, right. So, A is a 4 into 4 matrix, right, B is 4 into 1 and gamma is 4 into 1, right. So, this equation can be written in this form, that x dot is equal to Ax plus Bu plus gamma p, or this gamma, rather than using this gamma p, right. So, this is actually in the state variable form. Now, we can write x dot is equal to x plus bu plus gamma p. So, this is equation 17, or 4 state variables are there, x1, x2, x3, x4, and this is our A matrix, right, this is A matrix. Now, how we will know that system is stable? What we will do is that for A matrix you find out the eigenvalues. If all the eigenvalues real part lie on the left half of the S plane, then your system is stable, right. And B dash, that is transpose 0 0 0 1 upon T G, and gamma dash, that is transpose minus K P upon T P 0 0 0, right, and P is equal to disturbance, that is delta P L. So, this equation whenever we are writing your P, this P gamma P, P actually is a delta P L, right. So, figure 12 shows the dynamic responses for a step increase in load demand. So, I will show you the dynamic responses, just hold on, right. This is actually figure 12. So, this response actually for although steady state error remains same, but this continuous line, this is for reheat turbine, right. And when when the transfer function your what you call is dropped, the 3 into 3 model, this is for non reheat turbine, the dashed one, right. And frequency deviation for some parameter it is given, right, reheat and non reheat. Steady state value is same, but for reheat case peak deviation is more as compared to the your non reheat one, right, but the steady state value will remain same, right. So, this is the diagram. Now again I will go back to this one. This is our your what you call A, B dash and gamma, and this is the. So I showed you the dynamic responses also, right. Now another thing is that before moving to that fundamentals of automatic generation control, another point is that we know that x dot is equal to A x plus B u plus gamma p, right, and the responses which was shown, that is when u is equal to 0, there was no control signal, right, u is equal to 0. That means my x dot is equal to A x plus gamma p, and the responses was shown for p is equal to delta p l, and it was taken as a 0.01 per unit, 1% step load change, right. Now you from final value theorem you can easily find out the steady state, or what you call the steady state values, right, for all the state variables. But here also from this equation also, when your system is uncontrolled, you also can find out the steady state values. How? Now at x, so when u is equal to 0, x dot is equal to x plus gamma p. So I will write here, when u is equal to 0, x plus gamma p, right. Now your x is equal to, at steady state, x is equal to x s s, that is steady state value. That means x means all the state variable, that means x 1 s s, x 2 s s, x 3 s s and x 4 s s, right. So all the steady, or what you call steady state value of all the state variables. Now when all these things reach to the steady state, so what will happen to the derivative? Derivative will be 0 when they reach to the steady state, all the state variables. So that means so that means we can write down again that x dot is equal to x plus gamma p, but x is equal to at steady state, x is equal to x s s. So we can write here, then you substitute x s s dot is equal to x s s plus gamma p, right. But at steady state, that all the state variables derivative will be 0, that means this one should be is equal to 0, right. That means x s s is equal to minus gamma p, right, or multiplied both side by A inverse, then x s s will be minus A inverse gamma p. That means that if A inverse exists for any system, for this all the steady state value of all the state variable will be known. So simply if you can put it in your MATLAB, and if A inverse exists for the system, then x 1, x 2, x 3, x 4, n number of state variable steady state value, all will be calculated, all can be computed using this formula, x s is equal to minus A inverse gamma p, right. So this is the way how we can do it, right. So next is the fundamentals of automatic generation control. So with the primary speed control action, actually primary when primary controls later we will see primary speed control action, a change in system load will result in a steady state frequency deviation. That means if the primary speed control is there, that is governor loop parameter r, so you for a step load disturbance there will be a frequency deviation. Frequency deviation means, suppose initially it was operating your at f0 is equal to say 50 hertz, right. So after load disturbance it is not making the deviation to 0, it is showing some value, say some delta f is equal to, say we got minus 0.01 hertz, right. So this is delta f, that means what is the frequency at steady state? So frequency at steady state will be f0 plus delta f, right, that is equal to 50 minus 0.01, right. So this is your what you call that your frequency, right, but that means it is not exactly at 50 hertz, but it is less than 50 hertz for an increase of the load. Same will happen for a decrease of load, that frequency will increase, right. So depending on that value of that your what you call the droop characteristic of governor and frequency sensitivity of the load, that is the D parameter, it depends on the R and it depends on the D, right. So, restoration of system frequency to nominal value requires supplementary control action, right, which just hold on. So, your what you call which adjusts the load reference set point to the speed changer motor. Therefore, the problem can be subdivided into fast primary and slow secondary control modes, right. The fast primary control counteracts the random load changes and has a time constant of the order of few seconds, right. So, primary control actually your what you call your little bit faster one, right, and has a the slow secondary control, that is a supplementary control with time constant of the order of minutes. It actually regulates the your what you call generation to satisfy economic generator loading requirements and contextual tie line loading agreements, that we will see later. The primary objective of automatic generation control, that is AGCR, to regulate frequency to the specified nominal value and to maintain the interchange power between control areas, that means at the schedule value by adjusting the output of selected generator. That means many power systems are interconnected together, right, and they have some schedule interchange power, that is that through the interconnected lines we call tie lines, right. So, this function is commonly what you call that by adjusting the output of selected generator. So, this function is commonly defined as load frequency control, right. A secondary objective is to distribute the required change in generation among various units to minimize operating cost. That means, idea is something like this: when suppose when economic load dispatch is not there, so automatic generation control is equal to load frequency control, we can tell. But suppose you have a few control interconnected areas, suppose in a particular area there is an increase of load demand say 100 megawatt, and suppose you have 3 or 4 different generating units. So, from economic load dispatch you know that to minimize the fuel cost, that 100 megawatt you have to you are optimally you have to distribute among all the generators from the economic load dispatch such that your fuel cost is minimum. So, if that your what you call that your apart from your this load frequency control plus economic load dispatch is equal to your automatic generation control. But if economic load dispatch is not there, then we call it as automatic generation control is equal to load frequency control, right. So, much more will come, but before that we will see simply example. So, a system consists of 4 identical 400 MVA generating units feeding a total load of 1016 megawatt. This is 1016 megawatt, right. The inertia constant H of each unit is 5 on 400 MVA base. So, inertia H means it is in second, right. The load changes by 1.5% for a 1% change in frequency. This also we have seen how to find out R. When there is a sudden drop in load by 16 megawatt, this was 1016, this is 16 megawatt, just to make that easy calculation, right. You have to obtain the system block diagram with constant H and D expressed that 1600 MVA base, because there are 4 units and 400 MVA. So, 4 into 400 it will be 1600 MVA base, and determine the frequency deviation assuming that there is no speed governing action, these two, right. So, first part is for 4 units on 600 MVA base. So, H is equal to actually 5 into 400 divided by 1600 to 4. Actually, here I have tried to, I have not completed the write up that basically this is actually HEQ into MVA base is equal to 5 into 400, right, into your 4, right. So, that will give you actually it is 5, right. So, we will go to the next page. So, assuming that F0 is equal to 50 hertz, right. Therefore, delta PL upon delta, it is given 1.5% change of load changing 1% frequency. So, 1.5% by 1%, that is nothing but 1.5 by 1. So, basically this term actually 1.5% of this one, right. I mean 1.5% of, because load drop is 16 megawatt, divided by 1% of 50 hertz, right. So, basically percent cancel. So, that is why written 1.5 by 1 and this is 1016 minus 16 by 50. So, that actually is coming 30 megawatt per hertz, right. Therefore, D is equal to delta PL upon delta F divided by the 1600 MVA base, because each generator 400, so 1600. So, if you put this one, it will be 3 by 160 per unit megawatt hertz, because megawatt is converted to per unit. That is why to represent that writing per unit megawatt per hertz, right. We know Tp is equal to 2H upon dF0. So, H is known, D computed, F known. So, Tp is equal to 32 by 3 second, right. And in the second case, that with delta Pg 0, that no speed governing action means delta Pg is equal to 0. Therefore, block diagram will be simply delta Pg 0. So, if you go back to the block diagram, it will be minus PL, because when you see the block diagram, no speed governing action, right. So, this is plus delta Pg, this is minus delta PL, and this is Kp upon 1 plus STP, right, and this is our delta F. So, from there one feedback has gone to the governor, but no governing action. So, delta Pg is equal to 0. Therefore, this minus delta PL, and that is why it is given minus delta PL Kp upon 1 plus 1 upon Kp upon 1 plus STP delta F. So, Kp is known, 1 upon D, Tp is known, right. Then load change is your delta PL is 16 megawatt. So, base is 1600. So, 0.01 per unit megawatt, and it is a step decrease. So, delta PL will be 0.01 upon S because of step input, right. And find the from the block diagram, this one will be this one, and what you can do is you take the inverse Laplace transform. If you do so, it will become minus 0.01 Kp e to the power minus T upon Tp plus 0.01 Kp, right, or delta Ft is equal to, put all the data, it will be 1.6 upon 3 1 minus e to the power minus 3t upon 32. This is the answer, and at t tends to infinity. So, delta FSS will become 0.53. This is a steady state error, right, and this is your what you call delta Ft versus delta FSS. This is the plot, right. So, this is the steady state value, right. So, load increase or load decrease, whatever it is, that you can do it easily. This is a special case, this is a special case, right. So, thank you very much, we will be back again.